Okay. Okay.
Swaps the wire.
Oh, did I step on it?
Yeah.
Oh, lame. Okay. Oops. Anyways. What am I? Oh, here. Okay, anyways, so Go, right, we have to, there's no real solution, right? So in chess, if I have some chess, right, chessboard, right, if I have like some queen over here and some, I don't know, so you're king, right, you can just move forward and eat them and just go in circles and stuff, right? Just pretend this was the board, right? There's always going to be a solution for chess. There's some optimum solution, okay? For Go, there is no solution. Well, there is, but you have to, it's too much computational power, right? So if, for example, what is it? Oh. For example, question 1 is, where should I start on the board? Right, so that means you have to evaluate, right? So if it was for Go, you have to start from the first node, right? So this is your starting position, right? And you need to right? So you need to check every single one for the best for the best reward, right? So you have to branch out all of them, and so on. But I don't know how many boxes there are on the board. Let's just say there's 100. Okay, let's just say there is 100 boxes on this board. Check all 100, right? So step 2, we have to check all 90, right? So for each of them, we have to check 99, and then 98. Right, so for each branch, there's 100 branches. All of the 100 branches have to check 99 times. Right, there's 99 branches out. So as you can see, this monstrosity will get, this is horrendous, right? You have to check, I don't even know how many times you have to check. But you have to check so many combinations of every single one. So if you do, I think if you do the maths, I think that's 100. Oh, I can't remember, I don't know. So it's 99 to the power of 100. Right? Oh wait, no. It's 99 times by 100. Anyways, it's a very big number, okay? Some like trillion something. They said it was even larger than the number of atoms in the whole universe to calculate. So then the question is, how did AlphaGo actually win? Right? So how come they can calculate all this? So what they did is they used 2 different networks. Right? One is called a policy network. And one of them is called I think it was called evaluation. Or maybe action, I can't remember. Anyways, a policy network is to do this, right? To check what's the most optimum solution, right? And you'll think, how did they actually, check which one, right? So they had to use a reinforcement learning algorithm to find which of the branches should they only use, right? So delete all the rest and only check one branch, right? So they also use Monte Carlo methods, Monte Carlo tree search. Anyways, they use lots of stuff, right? And they can find the most optimum move for a player, and so on. Okay, so this is what they did in chess as well. Okay, but the point is, they made a new network called an evaluation network, and the evaluation network, right, gives you a score of how much percentage you're going to win or lose. So maybe it outputs a score of 50% that you will win. Right, so this is actually the hard part, to actually give a number to a game. So if you give the system, if you give AlphaGo a game, like a layout of a game, right, some layout, it can give you a score of a percentage of the player 1 winning. Right, so it can say player 1's going to win 25%, right, with this system. Right, so this is actually the hard part, actually evaluating the board, just giving it the board and it gives you some number. So that's what AlphaGo did. So I heard AlphaGo is trying to use their system. So this is not, AlphaGo is it's not just used for playing games. They put it in, so if I have, so remember DeepMind, right? DeepMind is a subsidiary, right? Google bought them, and DeepMind owns AlphaGo. So what they did is they used AlphaGo, right, and optimized Google's data centers, right? So Google has lots of data centers. Right, there's big, you probably saw it on the internet, there's big Blanqui servers, right, there's tons, literally it's like a library of computers. So what they did is they used AlphaGo to optimize the electricity usage of the servers. And they managed to reduce the energy consumption by 30% for Google, right, that's a lot of savings. And I think they said that, I think I heard they're going to use this system in UK for some energy reduction also. I hope they use it in Australia. But yeah, they're using this everywhere to do energy reduction. Because you can treat, remember we showed you a game, the fan and air conditioner game? It's kind of the same. So you can just, you treat it like a reward and it can learn the best parameters for reinforcement learning. Okay, next topic. It's a bit different now. Quantum computation. Okay, so you probably heard all the hype about quantum computing, right? So remember, quantum computing is so if you have some, remember a classical bit is 0 and 1, right? So in a computer, a classical bit can be either 0 or 1, right? So computers are all binary, right? You see in the shows, right? On the computer screen, they show all this junk like zeros and ones and so on, right? That's what a computer is coded in. But a quantum computer is when you have a quantum bit, right? And it's not a conventional bit, as in it can be 0, right, and 1, and also 0 and 1 at the same time. And what this means is that it can be in multiple states, right? So something like this. I think this is, yeah, some value. So this means state, right? This is state 0, and this means state 1. So I think you probably heard on the, I don't know, people keep talking about how quantum computing, it can be 0 and 1 at the same time or something. And all this means is that it can be in one state and the second state in the same time, where A plus B has to be equal to 1. Right, so it can be 0.1, 10% of a state 0, plus a 90% of a state 1. So that's what it means, right? So that's quantum computing. Right, this is, you're not allowed to change. Right? So you can actually phrase classical bits as a quantum system, but A and B can only be 0 or 1. Right? You're not allowed to change the system. It can either be 0 and 1. Right? It can be 1 and 0. That's all you can do. But a quantum system, you can actually change these probabilities or these distributions up. Okay, so anyways. So as you know, quantum computing can increase computing by I think they say quadratic fold. But yeah, it's crazy. They can increase computation time by quadratic. So what it means, oh yeah, because of the complexity. So what quantum computation can do is that if you have some maze, so if you have some maze, right, an old way to solve the maze is if you have some system, you just trial and error, right? If I go here, let's just say, yeah. Let's just do that, right? If I go over here, oh, it's a dead end. Start again. I'll start from here. Let's go in here. Let's say that the end point is here. Oh, it's a dead end. Start again. Oh, I win. Right? So, how many checks do we need to do? Approximately 3. Right? So what quantum computation does is instead of trying from the beginning, right? If I have some maze again, I don't start from here and from here, right? It looks the entire parameter space, right? So at the same time, right? So treat these as quantum computations, right? So it checks this one, checks that root, right? It checks this root, it checks this root, right? All at the same time. Okay, so it checks all these roots at the same time. And as you can see, quantum computation is crazy, right? If you can check stuff at the same time, you can increase computation speed by lots. So the question people had, I think, well, mainly what I had was, if I can do this with mazes, am I allowed to check the entire parameter space for machine learning? Right, so remember what machine learning tries to do is we need to update parameters. Right, these are your parameters. Right? But the question is, if I have some neural network architecture, right, that looks like this, is this good or is this good? Or is this good? Right? You can have multiple different model layouts, right? Or is not using neural networks good? Maybe you have to use random forest and stuff. Anyway, so the question is, can quantum computation check all of these systems at the same time? Right? Because if you extend quantum computation, right, you can check this, check that, and check this all at the same time. And I think someone answered on Q and Quora, I think they said no. So I don't know. But yeah, those are the questions people will ask, right? How can we use quantum computation in machine learning, right? So this is called quantum machine learning. You can also just search this up if you like, right? You phrase your machine learning problem as states. Oh, also, I think we were talking about, so if you did some maths and stuff, you'll probably hear, so you know quantum complex numbers, right? Complex numbers, right? The imaginary number I, right, is equal to root -1, right? So I think we were asking, how come in machine learning there's no complex numbers? Right? In machine learning, you won't ever see complex numbers in machine learning. Right? There's no negative root I. There's never root -1. Right? There's never I inside machine learning. For all the algorithms, right? Look, if I have a gradient descent algorithm, right? Even for all the variants like atom optimizer, you will never see something like plus I something. Right? Plus I something. And so the question is, why is that? How come people are not using complex numbers to its potential, right? Because you can just use the real part, right? So, in fact, people are trying to start using complex numbers. And for complex numbers, you can kind of have like some experience of like where you're pointing, right? If I'm learning some data point, if I have some data that's a vector from here to here, right? It can learn this, the system, without complex numbers, you can learn it, right? But it doesn't actually tell you where the arrow is actually pointing, right? This is always pointing this way, right? So if you use complex numbers, plus I something, right? You can actually work out where this arrow is pointing to. So that's what complex numbers is used for. I think people are trying to implement this. I think there are some people who are actually using complex machine learning, right? There's multiple complex numbers machine learning. You can also search it up, right? There's quantum computation machine learning. There's complex numbers machine learning, right? There's tons of different stuff. Yeah. Okay, a few more stuff. Okay, so dimensionality reduction. What is dimensionality reduction? Okay, so if I have some data, right, that is 200 columns long, right, and 10 billion rows. If I learn an algorithm on this will be crazy, right? Your total resource usage will be like horrendous. I don't even know, like 10,000 watts per hour or something, or 100,000 watts. I don't know, but it's crazy using gradient descent, right? So people try to reduce the number of columns, right? Don't reduce the number of rows. Rows are important, but what they do is they try to chop the number of columns, right? So that's what's dimensionality reduction. In dimensionality reduction, the first one is called feature selection. And what's feature selection? Feature selection is trying to find what's the most important columns and just delete the rest, right? So let's say there's only one important column, right? So you have to use a feature selection algorithm to select the best columns, right? So you don't have to check all 199 columns. Delete all of that. The second one is called feature engineering. And what is feature engineering? If I have 200 columns, right, so what 200 columns means is that this is a 200-dimensional plane, right? There are 200, the real number line is 200, okay? So that means you can't even visualize it, right? It's 200 dimensions. So what this tries to do is it tries to develop some system to reduce the number of dimensions to like 10. Right, so this is 200 plane to reduce it to 10 dimensions. Okay, so that's feature engineering. We're trying to reduce this to that. And what are some methods to do it? You probably heard of PCA, maybe. Right, principal component analysis. There's also TSNE. I actually forgot what that, can't remember what they stand for. But you can use these methods to do dimensionality reduction, which is to reduce the parameter search to increase computational speed. PCA is also related to SS something. Can't remember. Anyways, PCA is also related to some other algorithm you probably did in uni. But yeah. Okay, finally, the cutting edge of neural networks. Okay, so remember, neural networks, so this is the, yeah. So if I have some neural network, yeah. Okay, this is a neural network, right? Your X goes in and your Y comes out, right? And this is the black box, right? People say neural networks are a black box because we don't know what these numbers actually mean, right? What does a 0.8 mean, 0.9, what do they even mean? We don't know, right? So we call the middle part as a black box. We can't explain the algorithm. Anyways, so there are multiple, okay, so normal machine learning just uses gradient descent, right? And remember your activation functions. Remember the activation function? We gave you two examples, the sigmoid, which looks like this, right? Which is 1 over 1 plus e minus x, right? Which looks like that. It squashes all values from 0 to 1. And the other one we showed you was called ReLU, right? ReLU squashes everything below 0, everything like that's negative gets to 0, and everything else is just linear, right? Looks like that. Right? There are actually other activation functions, right? ReLU is the one you should always use. And probably sigmoid. But ReLU is the one for machine learning. This is the wonder of machine learning, ReLU, right? However, you may be wondering, why does it just squash to 0? Right? Maybe we shouldn't do that. So people are using now something called PRELU, right? There's also leaky ReLU, right? And these variants, instead of making it go to 0, it maybe makes it like this. It does that, right? It's a linear function that keeps decreasing like some small variable, right? Some small distance. And this is maybe more important than just normal ReLU. Remember normal ReLU is just delete everything that's less than negative, right? PRELU and leaky ReLU tries to increase like negative numbers, maybe like 0 point, like negative numbers like that, right? So those are the two which are very important. You need to search that up as well. And finally, the most important stuff for machine learning, right? The things which make machine learning work currently in modern world is called regularization and batch normalization. Oh, and also dropout. Right, so dropout is if I have some neural network architecture, remember they're all fully connected, right? All of these things. What happens if I just accidentally delete one? Like that. Just delete one entirely. Right? So that's called dropout. Dropout tries to reduce overfitting. Remember I said that we can't explain the black box algorithm. So instead, we're trying to reduce the complexity of the black box by deleting certain neurons, right? Just delete it entirely, like temporarily. And that's what dropout is. Right? You can also, if you check that out, dropout is the things that makes machine learning algorithms get over 99% accuracy. Dropout is extremely important for reducing overfitting. Right? Batch normalization. Batch normalization is trying to, so if remember, black box, right? Put something in, some layers, whatever, I don't even know how many layers. Right? What batch normalization does is within the layers, right? Within the layers, it tries to get the output of each layer between a number from 0 to 1. Right? Remember, normalization says that if I have like 100 and 200, I try to fit these two numbers on a number line from 0 to 1. Okay, so maybe 100 is 0 and 200 is 1. So that's what that's what normalization does. This is normalization. Batch normalization is normalizing the hidden layers itself, right, within this black box. Okay, so you're actually normalizing the layers inside. Right, so each step you're normalizing. You keep normalizing, normalizing, normalizing. Very, 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 very useful and important. So this is very important. This is also very important. And yeah, and regularization is just another method which you should just search out. Yeah. I think that's all. Thanks. Oh, yeah, you're gonna.
Nine.
Oh, did you work out the complexity? The number?
Yeah, I think it's this.
So as you can see on the side, right, after 5,000 iterations, you can see the game is most likely playing 16 days, 16 days, 16 days, 15 days. Right, the score is on the side. and the average energy cost. So yeah, the reinforcement learning algorithm converges.
That's the number of checks you have to do for Go. For Go.
Yeah, so n plus n minus 1, n factor. Oh, yuck.
So that's also optimizing for the enemies.
That's assuming 100 squares, so you made that up, right?
Yeah, so just change it to n minus 1, n minus 1, n minus 1. Wait, that's hot. That's disgusting.
9 factorial, isn't that like?
Yeah, that's crazy.
Like more than anything.
Yeah, that's more than the number of atoms in the whole universe. That's what they said. Yeah, nice. So it's a 100 factorial. Oh my god. Just times it all up together. You'll see it crazy. Your calculator would already be dead, right? So, yeah, but AlphaGo can like destroy this, right? It doesn't use that method. It optimized, yeah. Anyways, thanks a lot for coming to our 10-week-long lecture series thing.
Thank you.
Thanks.
We'll probably hold one next year as well.
Probably, yeah. For the AI lab things, yeah, I received your resume things. I haven't actually replied. Yeah, don't worry. It's in there. I have them. So the research stuff is, so these are actually real research stuff, right? So it's not like some easy stuff. So technically what I wanted you guys to do is, if you have time, think about the question and think about how you will solve it. It's not actually like a deadline. So it's more like a real PhD or honors project. So think about it over like 1 year. That's all.
The time frame, 1 year.
Actually, the time frame can be 2 years, because this program, like, it's a real question that has to be solved, and it's very hard to solve. So if you have ideas, just email me. Huh?
Text optimization, thing like that.
Yeah.
Filtering system.
Yeah, all of it is extremely hard.
James.
Like,